has invited my invitation to give actually some invited talk. I exactly asked him to give us a talk on a new generalization of generalized Petersen graphs. Yeah, that is my curious. It is the topic which I'm interested in, and I'm sure that it would be interesting for all participants of this workshop. So the floor is yours, and you are the first speaker of our day.
Well, thank you very much. I hope you can see my slides. Is that correct?
Yeah, it is correct. Yeah, we can see your slides. Yeah, everything is fine.
So, well, I would like to start with the important part, and that's thanking you specifically because, yes, you invited me to speak, and you even told me what to speak on. I also, I very much like this workshop. So far, the talks were very, very good. I hope it will continue that way. And I take advantage of this just to mention that we have a non-competing webinar, bi-weekly webinar. In fact, I think of it as coordinating and cooperating webinar, which you can find the information about at the webpage listed here. And our next talk, next speaker is Andrea Schwab, who will be talking on November 9th at 7 p.m. Central European time. It was pointed out already that it's kind of late for Novosibirsk, but I still think that at least you can watch the recording of the talk. So thank you again for inviting me. I'll start with a picture that's absolutely notoriously known for everybody in this workshop. The Petersen graph, and I will stress some of the properties of the Petersen graph that I might be interested in, or I will be interested in this talk. Of course, there are other properties. This, for instance, it's the smallest bridgeless cubic graph with no 3H coloring. It's the smallest non-Cayley vertex-transitive graph. We all know the automorphism group, but it has no regular subgroup. It's 3-arc transitive. It's the smallest cubic graph of girth 5, so it's a 3-5 gauge, which I'm interested in my parallel part of research into cages. It's connected vertex transitive, but doesn't have a Hamilton cycle. It's a 10-3-0-1 strongly regular graph, so that's another reason why people talk about this graph in this workshop. And this is just a minor thing that I will get back to because it's based on a relatively recent talk by Brian Eilspach in our webinar. So there is a subgroup of the full automorphism group that preserves a 2-factor and a 1-factor. The 2-factor being the outside and inside cycles, and the 1-factor being the spokes. So Petersen graph has lots of nice properties, and so it's absolutely natural to ask whether we can generalize this to a larger family of graphs while keeping some of these properties. It's kind of hard to keep all of them. For instance, we don't know an infinite family of connected vertex transitive graphs that don't have a Hamilton cycle. So I'm not promising an infinite family keeping all the properties of the Petersen graph, but I want to look into generalizations of Petersen graphs and ask questions of this type for the generalizations. So I will just take a very quick detour to a generalization that is not related to what I will be talking today about, but I just want to stress that you can generalize the Petersen graph in many, many different ways. So one of the ways is to remind oneself that the Petersen graph can be viewed as the graph whose vertices are the 2-element subsets of a 5-element set, and you join by an edge 2 vertices if they have an empty intersection. You still get the Petersen graph, and that this view allows you to generalize the Petersen graph in, as I said, in a direction that I will not go into in detail, but you can generalize into Kneser graphs. So those are the graphs where the vertices are the k-element subsets of an n-element set joined by an edge if disjoint. So this is a direct generalization of the Petersen graph. Special subclass, the odd graphs. The Johnson graphs, where you have the same vertices, but you join them if their intersection is of order 1 less than the size of the subsets. Or you can have the so-called merged Johnson graphs, where you have k element subsets for vertices and you join by an edge if the size is belongs to a prescribed set of sizes of intersections. And each time you can ask this type of questions: which of these are vertex transitive, which of these are Cayley, which are non-Cayley, which are, say, SR transitive. So these families may or may not consist of graphs that share most of the characteristics of Petersen, but you can always ask, so which members of the family do or do not? For instance, with Gareth-Jones, we asked the question, the Cayley or non-Cayley for Murch-Johnson graph, and we actually answered a large part of this. You can also look for small graphs of small girths, or large, actually, I should have said small graphs of large girth, and strongly irregular graphs. So this was, though, a detour, F1 to invariant graphs. I will get back to this, so you will see a definition of that. This was a detour in one direction. The other direction, and that's the direction I do want to follow in this talk, is to generalize the Petersen graph in a easy way, and let's call it an arithmetic way. So I want to define a generalization where the adjacency is determined by some arithmetic over a modulo n, over n or something like that. So I assume everybody knows this definition, probably more than any other. So this is the generalized Petersen graph, and it's given by two parameters, n and k, and that's all. You need to know, you need the two numbers, and then you have a specific generalized Petersen graph, and there are two sets of vertices. There is the outside cycle and the inside cycle. The outside cycle is a real obvious cycle where the neighbors are joined. Then there are the spokes, which are these guys here, and then there are the inside edges, and those do not have to necessarily form a single cycle, but they are decided based on modular arithmetic. So what I like about this generalization is its compactness. It's very, very short description. You get two numbers, and then you know which graph you're talking about. And I think that's the direction I want to keep. And in fact, that will be the generalization I will be talking about. So this is what I'll be trying to do, to generalize the Petersen graph while not introducing too many new parameters, and still asking the types of questions: which of these are Cayley, which of these are vertex transitive, non-Cayley, and this type of questions. So let me just very briefly go over the results for generalized Petersen graphs, because it's good to keep these in mind when one goes to further generalizations. So already Frucht, Graver, and Watkins in 1971 determined that which of the generalized Petersen graphs are vertex transitive, and it's if and only if k squared, the second parameter, is plus or minus 1 mod n, or there is one exceptional one, the dodecahedron. And so this is known, and so it's very easy. If you get a pair of numbers, you immediately know whether the graph is vertex transitive or not. All you have to do is to square the second parameter k. Then a more precise result due to Nedelange-Koviera and Lovrečić and Sarajin from 1995. You know when these graphs are Cayley, and the answer is they're Cayley if and only if k squared is congruent to 1. So roughly half of this, or no, that's not correct, but only one gives you Cayley. And again, this is a wonderful result because it's very clear how to check. If you want a Cayley graph, you know how to take the parameters. And if you get the parameters, you immediately know whether it's Cayley or not. And there's one more result this is relatively recent based on the talk that we saw with Brian. So it's F1 to invariant, meaning there exists a 2-factor and a 1-factor which are preserved by the full automorphism group. So this is a subset of the Cayley generalized Petersen graphs. So almost all of them, when k squared is congruent to 1 mod n, with these few exceptions. So These are the types of questions you want to ask once you generalize the generalized Petersen graphs. Which of them are vertex transitive, which of them are Cayley, or which of them are F12 invariant. So again, two observations that I will try to discuss further for the generalizations. So the vast majority of generalized Petersen graphs are not vertex transitive. So yes, we have a wonderful family, but the majority of them are not vertex transitive. And a large part of the vertex transitive generalized Petersen graphs are Cayley. A significant part of the vertex transitive generalized Petersen graphs are Cayley. I don't want to go into precise numbers because that's basically number theory, but it would be meaningful to ask what's the precise proportion of the Cayley generalized Petersen graphs versus the all vertex transitive generalized Petersen graph as the order increases to infinity. But that's basically number theory. Okay, one more detour, one might say. This idea that you just have a bunch of parameters and that gives you a nice graph is not just mine. Many people have tried this. The Rose window graphs by Steve Wilson are tetravalent, so not cubic anymore. But you can see that it's a similar idea. You have the outside cycle, then you have the inside vertices, and you have so outside cycle, spokes, and then you have for each of the inside vertices, two neighbors in the outside vertices determined again by modulo arithmetic modulo n. So again, this is a natural generalization, and we will be seeing this a lot in the generalizations that you keep maybe one of the cycles, so you keep the spokes or something, and then you decide some few other edges based on modulo arithmetic. Again, for this class of graphs, we know which are the edge transitive Rose window graphs. That's due to Kovac, Kutnar, and Marušić from 2010. We know which are vertex transitive Rose window graphs. We don't have this completely simple kind of a description. There are infinite families, but it's still, we have a precise description of which of them are vertex transitive due to Dobson, Kovac, and Miklavich. And Das and Mandal classified vertex transitive Rose window graphs, which are Cayley. So I'm also listing these results to convince the audience that these are the types of questions that people like to ask for these graphs, which are not very far from the generalized Petersen graphs. So another topic that everybody knows, but I will just mention so that we have it clear. A non-identity automorphism of a graph will be called Mn semi-regular if its cycle decomposition consists of m cycles of length n. So the first number is the size of the cycles, the number of cycles. The second number is the length of the cycles. If I was inventing this notation, I would go the other way. I would start with the length first, but we can remember. So m is the first number. How many cycles of length n are in the automorphism? Okay. And graphs admitting Mn semi-regular automorphisms are called M-circulants. And so just for the language, bi, tri, and tetracirculants are for the, for one, it's circulants. Yeah. So this is known, and generalized Petersen graphs are definitely bicirculants. It's absolutely obvious that this rotation around the center of the graph is forming two cycles of length n. I should say clearly that not graph cycles necessarily, but cycles of the permutation. The inside doesn't have to be a single cycle, but it's a cycle of the permutation. Okay, so semi-regular automorphisms out of the way. Generalized Petersen graphs are all bicirculants. And next, I will go into some few generalizations of generalized Petersen graphs that are known from previous research. So in 1988, in the Foster census, the I-graphs were introduced. And again, the idea is still the same idea that I started with, and that is you want to describe the graph with a very small set of numbers, possibly, and using arithmetic modulo n. So you have, again, two sets of vertices, the outside and inside vertices. You have the outside, you have the spokes, but the outside cycle is not the one defined by UI plus 1, but you select, for the outside cycle, you select the size of the jump that you take. So this, and of course the inside is the same. So I have two parameters, j and k, instead of just the k previously. But it's obvious what these guys look like. There is an outside cycle or a family of outside cycles. There is a family of inside cycles or an inside cycle. And then there are the spokes. So very, very, very natural generalization. If you look for generalizations that will produce vertex transitive graphs that you have not seen before, then this is not the one, because it's known that the only I-graphs that are vertex transitive are those original generalized Petersen graphs. Because of course, when you choose J to be 1, then you get a generalized Petersen graph, and some of these guys may be isomorphic to them, but still, if an I-graph is vertex transitive, it's isomorphic to one of the original generalized Petersen graphs, which are isomorphic. Okay, so it's a nice generalization, and if you look for other properties than vertex transitivity, then of course this may be a family to use. But if you look for new vertex transitive graphs, then this is not the way to go. Okay, another example of this kind of an approach is due to Lovrecic, Sarajin, Paco, and Previtali, who introduced the super generalized Petersen graphs. In this area, when you come up with a new family, the very first thing is you have to come up with a name, and it's kind of complicated. Super generalized is already used, and I'm not sure I like the name, but so here's a super generalized Petersen graph. So you have two parameters, m and n, and you have m additional numbers, and you have the edges. You have the edges defined again via modulo arithmetic. I will not do this in detail. This can be, of course, checked, but it's basically the same idea, but you have more numbers to deal with. Okay, and this family actually contains the generalized Petersen graphs as a subfamily. So that's a proper generalization. Yeah, and many things can be discussed for this family. Okay. Another example of this type of an approach goes to Kondor, Pisansky, and Zhitnik, 2014, who introduced the GI graphs. I'm not sure what the abbreviation stands for, but again, the idea is that you have a bunch of numbers that define the graph, and all of these now have Zm cross Zn. Well, the last two have Zm cross Zn for the vertex set, and you do modulo arithmetic, modulo m, and modulo n. So these are called the GI graphs, and as I said, they are due to Kondor, Pisansky, and Zhitnik. And the case m equals 2 covers the I graphs, and also when you take n1k, you get the generalized Petersen graphs. So these are all genuine generalizations, and also generalizations of the I graphs. Okay, so instead of checking the definition, here is one example. This is an example that's both a GI graph and a super generalized Petersen graph. So it looks a little more chaotic than the generalized Petersen graphs, but it's very clear that there will be many symmetry properties and things that one can check for. Okay. One more generalization before mine or I shouldn't say mine, this all this that I'm talking about is a joint work with Tomo Pisansky and my former diploma student Katarina Jasenčáková, who's now done with her PhD. So it's not just my results that I'm talking about, and but this is a generalization of generalized Petersen graphs that's not due to us. These are called the double generalized Petersen graphs, introduced in 2012 by Zhu and Feng. And I'll just give you the picture because, again, the idea is the same. It's just slightly more complicated. You have two cycles on the outside. Then you have the spokes. You have two sets of inside. And then here you determine who's joined by who. So these are this would be the DP52 graph. Okay, so clearly people have tried various possibilities how to generalize the generalized Petersen graphs, and for each of the families, one can ask the questions of the type, which of them are vertex transitive, which of them are Cayley, and this type of questions. So in the next few slides, I will introduce our family, and I already advertised what the motivation behind the family is. And I will introduce the family with a reference to a talk by Brian Alsbach, who talked 2 weeks ago or 4 weeks ago on F12 invariant graphs. And it happens so that it's a very good introduction into our family. So I will do it, although it's historically not correct. Our construction precedes Brian's explanation of it, but here it is anyway. So this is from Brian's talk, which are the F12 invariant graphs. So a cubic vertex transitive graph is called F12 invariant if its edges can be decomposed into a 2-factor and a 1-factor, and the partition is preserved by its full automorphism group. This is important, the full automorphism group. Okay, so the idea is that I have sort of, but this I'm oversimplifying. I have sort of the spokes, which is the 1-factor. So it's a perfect matching, and then I have some system of cycles. Yeah. And this system of cycles is the 2-factor. And I want graphs where the full automorphism group sends spokes to spokes, and it sends the edges of the 2 cycles to edges of the 2 cycles. And if you start discussing this kind of a topic, the very first thing that comes to mind is you study the case where the 2-factor is a Hamiltonian cycle, and you quickly get rid of that. That is well understood. That must be a circulant. And then you start discussing the possibility when one of the cycles is half the size of the graph, half the order of the graph, and the other may or may not be a single cycle. So what do things look like then? So once again, think of this as an introduction into the construction that I will be talking about, into the generalization I will be talking about. So you have an outside cycle, you want to keep that. You have the spokes, so here's the picture. You have the outside cycle, you have the spokes, and here you want to introduce something so that the result is cubic, and you want that it's preserved by the full automorphism group. Okay. So Brian discussed this in his talk, and this is really a slide from his talk. I just copied from his talk, and he talks about the following family. It's a graph where you obtain by starting, the cycle and the spokes, and then you add the edges I plus A, I plus B. These guys inside. It's I will give you a precise definition of our family, but this is a nice example of a member of our family, and it sort of looks like, if you want to think about it that way, that you have 2 types of adjacencies for groups of 2, because this is repeated now. Yeah, the groups of 2 are the same in a way, and that's exactly our definition, which we ended up calling group divisible generalized Petersen graphs. because we wanted our name to be different from all the previously used ones. And it really makes sense. So the definition is as follows. You choose the number n. The graph will have 2n vertices, and the outside is a cycle. And then there are the spokes. So the outside is a cycle. Then there are the spokes. And then you have a set of m numbers, which determine the neighbors within the inside vertices. And they don't go the way that the generalized Petersen graphs went, and that is in the generalized Petersen, you always added the same number. No, this time we split the inside vertices into groups of size m, and the first guy in the group gets added the number k sub 0. The second one gets added k sub 1, and so on. So and then you start repeating for various groups of size m. You do the same thing. There is a little bit of a requirement that you have to add in order to be sure that the graph is cubic. But other than that, this is the idea. So group divisible generalized Petersen graphs, that's the topic of my talk. You construct an outside cycle, then you connect things with spokes, and here you divide things in groups. And this is my group. This guy was obtained by adding 1. And this guy was, well, the edge was obtained by adding 1. For this guy, it was obtained by adding 3. Again, moving to this group. This guy gets an edge by adding 1. This guy gets an edge by adding 3. I have 4 groups of 2 vertices. And I have divided the group of inside vertices into 4 groups of 2 vertices, and for each 2 I do the same, but I don't necessarily use the same addition for both of them. The group doesn't have to be just of size 2, it can be of larger size. This semicolon stops the information about the size of the outside cycle, and then the number of numbers following the semicolon decides the size of the group. So it would be the generalized group divisible generalized Petersen graph, where the size of the group is 2, n is 8, and I'm using 2 numbers to determine the neighbors for the inside. This most of you are already saying this looks very simple, but that's exactly the point. We only move a little bit away from generalized Petersen, and we simply allow for things to have different neighbors, but we still want to have repetitions of groups. Yeah, we could have, of course, think of the cases where everybody gets a different addition thing, but then we would lose most of the nice properties. So this is what we will stick to. It's not a bicirculant, which is very easy to see that it's not a bicirculant. You don't have an automorphism that takes, well, you have one that preserves this, but it's not a complete automorphism. So it's not a bicirculant, and therefore it's not a generalized Petersen graph. Obviously, this family includes the generalized Petersen graphs. So we have a genuine generalization, which contains graphs which are not generalized Petersen graphs and are still nice. So this is why we are interested in the family. So the first lemma is simply determining, and it's very easy, very obvious. So if your m, that's the size of the groups, is greater than or equal to 1, then you have a 2m n over m semi-regular automorphism, because you can rotate a group to a group. Yeah, so you can rotate by m vertices and you will get an automorphism of the graph. It's obviously an automorphism, and it has orbits of size n over m, and it has 2m of them. So for instance, when m is 2, then we're talking about groups, 4 groups of size n over 2. Okay, so but in general, these are 2m circulants for sure, and so that makes them interesting for people who are interested in k circulants. Let me just give you two more easy lemmas. That's always an advantage when you define a new family. You can start with some easy lemmas. So these graphs are bipartite if and only if n is even and all the elements in K are odd. Remember, K is the list of adjacent, the connecting set, if you wish. Okay. And then you also want to decide some isomorphisms because all of these graphs are not necessarily distinct graphs up to isomorphism. So you can have periodic sequences. So if your sequence is periodic, say twice the same set repeated, then obviously it's the same as if you took half size of the group and only used half of the connecting set. So we will always assume that our defining connecting this K is non-periodic. I don't have two groups of equal numbers following one after another. Okay, and so now we have our family defined, and we can discuss automorphisms and properties. So the first is, let's discuss the automorphisms. Here is an example. So n can be anything greater than or equal to 4. And I have two numbers in the connecting set, 1 and n minus 3. And this is a family that's already known. These are called crossed prism graphs. And here's the GDGP2815. So this is what it looks like. And you can see that there will be some symmetries. Okay. The first thing I have to always remind myself that some of these are Petersen graphs, so you don't want to spend too much time with those. Another example of the type from the previous slide is the Franklin graph. Again, something you have seen before. And all the GDGP2, N1, N-3 are vertex transitive. Okay, so we have a large family of vertex transitive graphs already when the groups are of size 2. And one of the numbers is 1, and one of the numbers is N-3. The 1 takes care of these edges, and N-3 takes it this way. So all of them are vertex transitive. So group divisible generalized Petersen graphs contain lots of vertex transitive graphs. And if you have an automorphism that the sets I call I I is the one factor of the spokes, and then you have the outside set omega, and then you have the inside set of vertices sigma. And if you have an automorphism that fixes these sets, then it either fixes all three sets, or it fixes sigma setwise and interchanges omega and I. So these are simple observations about what things can look like, the special things that that fix one of these three sets. So as I say, these are easy things. You just prove them by exhibiting the automorphisms, basically. Further results of this type, you can have a reflection that swaps pairs of vertices. Again, I guess I shouldn't go into the details, but all of this is in the paper, and all of these are relatively technical. My goal is, of course, to determine as many as possible, or which of these are vertex transitive, which of these are Cayley, and so on. So these are just partial results along in this direction. Okay, so as I say, I will not go into this, but under certain circumstances, you have specific automorphisms that swap pairs, or so these are partially involutions and so on. So you don't. Proofs are relatively easy. You just really exhibit the automorphisms, and it gives you a lot of information about the full automorphism group. So let me just give you an example instead of really carefully checking the theorems. So this is a graph where the groups are of size 3. And I have 3 parameters, A1, N-1. 1 and n minus 1 do this. And so 1, and this is n minus 1. And they all admit an automorphism fixing the vertex u sub 0, which would be one of these outside guys. Yeah. So you can have this, if you just check here, obviously there is an automorphism like that. Okay. So this is symmetric with respect to a reflection like this. I maintain these are easy observations, but you try to collect as many of them as possible in order to determine the automorphism groups of these creatures. Okay. I had a diploma student who in his master thesis just played with these with a computer and looked for some special things. So for instance, he noticed that there is a bunch of these graphs which have a very large automorphism group, n times 2 to the n over 2. So that's a relatively large automorphism group. Some other easy observation. These graphs are neither edge nor arc transitive. And there is an additional lemma based on his observations, but it's proved that if you take a graph with a group of size 2 and 1 and n minus 3, that's the family we already saw. It admits at least one automorphism which doesn't fit its set of spokes. So you can have an automorphism that mixes the spokes with the outside or inside edges. Okay. And I just give you the automorphism. It's really not. Again, this is based on his evidence, and then we were able to prove this to be in general. Okay. And we can actually, we can prove then the result that I already mentioned, that these graphs n1 and minus 3 are all vertex transitive for n greater than or equal to 6. So I already stated this result, but it's for the beginning, it's very easy to play with a computer and form conjectures. And then you get some small subfamilies carved out for which you already know they are vertex transitive, but you don't get the full picture. A further result along these lines is more general. So we have a situation where you have a graph that admits an automorphism that preserves the spokes and swaps the outer and inner vertices. Okay, so we preserve the spokes, but swap the outer and inner cycle. Well, it doesn't have to be a cycle. The outside is a cycle. And there are some arithmetic conditions when this may happen. And it's if and only if. And the conditions take a form of much more complicated congruences, but still congruences. And more complicated because I have two numbers. Yeah, so I can check if this and this is true, or this and this is true, and this is true, then I have a special automorphism, an automorphism that preserves the spokes and swaps the outer and inner vertices. And that one is interesting because that one allows me to go from the outside to the inside. And so I have a good way of deciding whether a specific automorphism exists. And if you look at the previous, these are pairs of congruences, but you can say that if they're satisfied, they also satisfy this. K sub 0 plus K sub 1 squared is plus or minus 4 mod n, or K sub 0 plus K sub 1 squared is minus plus 4 mod n. So what this means that is somewhat similar to the situation with the generalized Petersen. If I have two numbers defined in the graph and I take their square, instead of having the plus or minus 1, it appears that we have plus or minus 4 as quite relevant, but we don't have an if and only if and only if result of the type I was talking about by Frucht, Graeber, and Watkins. We only have one direction. So if I have a graph where the groups are of size 2 and they are defined by two numbers K sub 0 and K sub 1, and if these parameters satisfy this, the order of the element in Zn is n½ and one of the above systems, then I'm guaranteed to have a vertex transitive graph. So this is a way to get many more not only the 1 n minus 3, but further vertex transitive graphs for groups of size 2. And somehow they are defined in a similar way as the vertex transitive graphs for generalized Petersen graphs. And we say that it's a sufficient condition. If this is satisfied or this is satisfied, then the graph is vertex transitive. And I should also say not only these graphs are vertex transitive, but they are in fact Cayley graphs. So all of these that satisfy this are Cayley graphs. So as I said, in the case of generalized Petersen graphs, the thing was that we had this type of arithmetic condition, and it was an if and only if, with the exception of the dodecahedron. Here we have just one direction. If the parameters satisfy this, the graph is necessarily vertex transitive. So you naturally ask, are there graphs which are vertex transitive where the parameters do not satisfy this? And the answer, well, first of all, here is an example that is vertex transitive and satisfies the first set of congruencies. This is a nice graph. It's vertex transitive, and it looks like this, each group of size 2, and I'm adding a or n minus a plus 2. And in that case, I have the numbers the way I want, and the resulting graph is vertex transitive. So this is an example where it has to be vertex transitive due to the arithmetic conditions. But there are examples of vertex transitive graphs where the groups are of size 2, which do not where the parameters do not satisfy these systems. They are vertex transitive. Their inner edges form a single cycle. So the congruency condition that I presented is sufficient, but not necessary. So we don't have the nice situation in a way Watkins and the others locked out that the condition they found was sufficient and necessary. So far, we only have a sufficient condition at this point. Karl Ludwig, again, my student, played with the computer and found lots of examples, found examples which are vertex transitive and where the inner ring doesn't even form a single cycle. Okay, this may be a bit surprising to you that that doesn't have to be the case, that inside is a single cycle, but it also happens for Petersen, so it's not completely surprising. Smallest graph in this family is a graph which has 24 vertices and 1 and 3, and it's isomorphic to the Cayley truncated octahedral graph. So basically, I should maybe say what I'm doing. We're discussing the family that I defined, and we're discussing the situation when the graph is vertex transitive. And that's something that I believe is interesting for any such family. And here is something that is vertex transitive, but the parameters don't satisfy the congruency relation that I was expecting. And there are some other examples. So this is GDPG 1213, which is vertex transitive, but you can see that it's not even a single cycle inside, and here's another example. Okay, there are more examples that he found, but this is the complete list of what he found. Okay, so he was going all the way to n less than or equal to 300, but the only examples where you get vertex transitive graphs, where the parameters do not satisfy the sufficient condition, are here. So he found 6 graphs which do not belong to this family. So there are examples, and we don't have an if and only if, but if we can find out whether these are the only possibilities that are not covered by the congruency, and if we can figure out how to describe these guys in general, not just for vertices up to 300, then one could be possibly able to determine which of the GDPGs with n equal to are vertex transitive. If you look at these graphs, obviously you will see that 192 is twice 96 and so on. So Maybe there is a system to this, and I just admit we have not determined the system, and we do not have an if and only if at this point. Okay. If you ask the more specific question, which of these are symmetric, then you have much stricter requirements. And recall that if the group is of size 2, the groups are of size 2, then we have tetracirculants, 2 times 2. And there is a result by Freilich and Kuttner. A connected cubic symmetric graph is a tetracirculant if and only if, and we have a list of cases. So since all the GDGPs with the size of the group being 2 are tetracirculants, those which are symmetric must be on this list. So in that sense, thanks to the result of Freilich and Kuttner, one can determine which of the GDGPs with a group of size 2 are symmetric, meaning arc-transitive, for those of you who use the other language. And here's the complete list. These are finite lists, and then there are 2 infinite families. And in order to answer the question which GDGPs with the groups of size 2 are symmetric, you just have to compare with this list. I will just show you one example. The Dick graph, which is it's in the Foster census, it's F032.8. It's isomorphic to GDGP 21637. So this is a symmetric group divisible generalized Petersen graph, one of the examples. Okay, so those happen, but obviously due to this theorem, there will not be too many group divisible generalized Petersen graphs with groups of size 2. Okay, obviously this doesn't cover larger groups, because then I don't have the list of, because for larger groups we have like if the group is of size 3, it's a 6 circulant, and I don't have a classification of those. So this only goes toward those where the sizes of the groups are 2. Okay, and here is one example. I want to finish with open problems. And so some of these concern the group divisible generalized Petersen graphs. I swapped the PNG here. First of all, I should say I should have started the open problems with lots of problems that we have not solved yet for our family of generalized Petersen graphs. But I was very clear which are those. So I will finish with slightly more general formulations of problems. So my first question is, so what's the ratio between vertex-transitive GDGP graphs and all GDGP graphs? I pose the question in the form of a limit. So the order of the graphs goes to infinity. I consider all the graphs of order less than or equal to n in my family, which are vertex-transitive, and compare that to all the graphs which are in the family of order less than or equal to n. So vertex-transitive versus all, I guess it shouldn't be hard to prove that this limit is going to be 0, and the majority of the graphs will not be vertex-transitive. But I like to state questions of this type because I think that they give me, the answers possibly give me an idea what are the relations between the entire family and the vertex-transitive examples. You can also ask the following question: how many of the vertex-transitive graphs in our family are in fact Cayley graphs? Yeah. So this is again a very, very meaningful question because it addresses the question, so how often you get a non-Cayley vertex-transitive graph this way? And if this limit is 1, then the answer is not very often, because the absolute majority of all the vertex-transitive graphs in our family are Cayley graphs. So I don't know the answer to this. I really genuinely think these are open problems. What is the proportion of Cayley graphs within the family of all vertex-transitive graphs in our generalization? And the rest of the questions are more general. They don't concern just our new family, but I really would like to see one day these problems solved. So I will advertise. What's the ratio of Cayley graphs within the family of vertex-transitive graphs in general? Okay, so this, even if you think that our family is very special, this is an absolutely general question about vertex-transitive graphs. What is the proportion of Cayley graphs among all vertex-transitive graphs? Do they form the majority? So is this limit equal to 1? Or do they form do they gradually disappear sort of, and this limit is possibly 0? If one believes that fewer symmetries are more prevalent than more symmetries, then one would suspect that this should go probably to 1. But I don't have any kind of a proof. It's just a feeling that maybe the majority of vertex-transitive graphs are indeed Cayley graphs. And I really, really would like somebody to solve this, because I believe that understanding vertex-transitive graphs, if we want to claim to understand vertex-transitive graphs, we should be able to answer this question: how many of them are actually Cayley? And as I say, based on analogy that most graphs have no automorphisms, then most vertex-transitive graphs have only Cayley automorphisms. Maybe that's true, but I would like to see the answer to this. I can ask a more special question: how many of Cayley graphs are graphical regular representations? So to make it clear, graphical regular representation is a Cayley graph where the vertex stabilizer in the full automorphism group is trivial. So they only have automorphisms that come from left multiplication in the group. That's a class of Cayley graphs that was widely considered, and many things are known for them. But I'm just asking, what's the proportion? And this is not my question, by the way. This is a question that's been around since people studied the GRRs. The belief is that the limit is actually equal to 1. Okay, so if you take, sort of to translate this, if you take a random Cayley graph, with probability 1, it will have a trivial vertex stabilizer. So a random Cayley graph will have a trivial vertex stabilizer with probability 1. This is believed to be true. There are some partial results toward this, but we don't know whether it's true or not. So I'm asking, what is the limit 1? Is the limit possibly 0? I don't know. And I will finish with one more very closely related problem that maybe people who don't work with maps are not very much interested in it, but it's very close related to this series of questions. If you take all orientably regular maps, so that means all the maps where the orientation preserving automorphisms act regularly on darts, and you ask how many of them are Cayley maps, which is a very, very special subclass of maps, very, very special in the sense of the definition. But the question is, so what is the proportion? So Cayley maps are special embeddings of Cayley graphs. And again, I believe this question is related to the previous questions. And at some point with Josef Schirijn, we believed we had a proof that this ratio is actually 1, that almost all orientably regular maps are Cayley maps. But we don't have the proof, or at least we cannot recover it. We did it without pencil and paper. So this is still open, and these are the problems I want to finish my talk with, because these are the problems I'm interested in, and these are the problems I partially addressed in my talk about the new family that we discovered with Katarina and Tomo Pisanski. So this is all. I thank you all for your attention. Here's Tomo, here's Katarina, and I believe Katarina likes this picture better of herself, and Tomo is probably different. Thank you very much.
Okay, thank you very much, Robert, for this nice talk. Are there any questions to the speaker?
Hello.
Yeah, please.
Oh,
Kira, yeah, please, yeah.
It's a very early part of the talk, but I thought this. I want to see the definition of a rose window graph once again.
Okay, we can go there. Steve Wilson's definition. Okay, here. So, sorry.
Yeah. I thought there are edges connecting VIs to among themselves, so there should be inner cycle.
I don't know what to say. This is a definition from Steve Wilson's paper.
Yeah.
So.
Yeah, but I thought the VI is connected to VI plus R, not UI plus R.
Well,
the fourth,
okay.
Yeah, that one.
I don't want to argue because I may have made a mistake, but I was very careful and I copied the definition from Steve's original paper. So, and that paper is in the
AMC.
Ars Mathematica Contemporanea, so it's accessible. And if I made a mistake, I apologize. But I really tried not to make a mistake. So if you remember that they should be connected within between the VIs, I don't think I made a mistake, but
yeah, Steve Wilson called the inner vertices hubs. Yeah, hub, and there are edges connecting hubs among themselves. So
did I make a mistake? Then in that case, I apologize. So one of the
the last one should be V sub I plus R, not
okay.
U.
Then I apologize. So this last one should have been a V.
Yeah,
maybe I just mistyped, but I tried not to make mistakes. I apologize.
Sorry, you have the same misprint on previous slides on the definition general Petersen graph.
I have the same misprint.
Yes.
Oops.
Previous.
Even previous. Where? No, I always try not to make mistakes.
You are right.
I will double check, and it appears that I copied wrongly from.
Thank you very much for the interesting talk.
Yeah. There is one more question from Clara Strop, please.
Yes. So I wonder could you say something about the relation to group divisible designs, and also if you think this can be generalized to hypergraphs in some way?
I don't know a relation to group divisible designs. I just stole the name from there. I wouldn't try. I don't think there is a close relation to group divisible designs, but this may be due to not investigating enough. I just don't know. I stole the name and I don't know the connection because my gut feeling is that there isn't much of a connection. But it's also something that I did not pursue since. So Yelena asked me to talk about this. I still like the topic, but I didn't have the time to investigate all the connections, and I didn't have the time to finish the question, the classification of Vertextransitive. So I'd say everybody who's interested can look into this. I'm not at this point. I cannot do that, but my gut feeling is there is no connection to group divisible designs.
Well, I mean, for me, it's better if you don't have an answer. Yeah.
Okay, I don't.
Okay, are there any other questions, Robert? Well, actually, I have some questions, but I think that we have no time to discuss. And also, I have one more suggestion to give one more talk in 6 months. Well, actually, we have this workshop twice per year. So I would be happy if you can continue to talk about this topic or any kind of topics you would like to give a talk. Yeah.
I definitely promise to participate and watch talks. And if
okay, good, also, very nice. Yeah.
I can also give a talk.
Okay, very nice. And I will ask you my questions by email.
Okay.
Okay, thank you.